Hello everyone. So welcome to this video lecture. Um, so this is our first time that trying to do this. I'm sorry that I will be traveling, so this has to be made this by a video lecture. So hopefully you will have a very good learning experience. Uh, if you have any questions, any comments, please feel free to send me an email so we can um, have further discussions, or I can answer any of your questions. All right. So this lectures basically we will resume what we have been discussing since last couple of lecture, which is about TCP. So we had a lot of discussions about flow control mechanisms like um, stop and wait, go back in, and then the selective repeat, and so on and so forth. So I remember that last time we stopped right here at page 10 of lecture 11 slides. Um, so, um, so for TCP flow control, as we mentioned, it's basically some things that arrangement between the sender and the receiver. Okay, so in a lot of times when uh, you when the receiver, for example, has to advertise its the available uh, spaces in its buffer to allow the sender to send this amount, so that he's basically is telling the sender do not overwhelm me. So the receiver window, that header fields will be set. Specifically, it's called RWND. So you can see RWND actually is the receiver window size that the receiver tell you that you cannot exceed that one. I mean, in terms of the sending windows. I mean, you cannot send too many back to back without acknowledgement. All right. So as you can see from the right hand side of this figure, the receiver buffer always constant. It is always constant. That's the maximum buffers you can use, right? So, so as you can see, depending on how much buffer data is available in the receiver side, then the receiver window actually is you are available. You are available to be used for the sender. Then is RWND receiver window is always smaller than of our receiver buffer, right? So for receiver buffer is constant. Usually it's preliminary set by the socket. For example, 4096 bytes is a very common maximum receiver bus size. Okay, so you can see the receiver windows will always be dynamic. It cannot exceed the receiver buffer. All right, so it's kind of negotiate and coordinate between the sender and the receiver, limit the in-flight numbers of packets in the windows. All right, so by doing this, we can always guarantee that the receiver buffers will not be exceeded, and so the receiver will not be overwhelmed by this coordination, which we have been mentioning for many times. So hopefully you understand that. All right. So because the TCP is connection oriented, then we also mentioned before that we needed to establish some kind of connections. So we needed to do handshake. So usually handshake is a process to make sure each other understand each other. So they understand each other. So whatever the parameters you have to use to establish this connection, for example, the MSS, the maximum segment size. So it's basically you have to agree. The size of this has to be agreed between the receiver and the sender. All right, and then you have to agree about the sequence number, the initial sequence number you're going to use for both two directions, and the receiver buffer, right? So these are all done automatically for you when you try to create a socket and when you connect it to the remote socket. So from the client side, from the server side and the client side, after you run um, these two clauses, you will be able to establish this connection automatically for you. You may not notice this at all, but This handshake is kind of done at the beginning stages of TCP sessions. So basically purpose is to agree on some things, right? Whatever you want to use for the foreign TCP transmission, right? So now you will have a problem. So we know that we have to do handshake, but how to do the handshake, right? This can be tricky because handshake usually need back and forth communications to make sure the other side understand me, right? So either you can do it, for example, on the top, you can see we can do it in a two-way handshake, which is quite normal, quite common, and quite natural and straightforward, right? Or you can do three ways. I mean, at the end, you add one more confirmation uh, at the bottom, so you can see. So which way shall we do? All right, the two-way handshake or three-way handshake? So the deal is, it's not an easy decision. Actually, it's a very straightforward or intuition you may have is two-way handshake should be enough, right? So for example, Alice requested to talk, and Bob said that okay, I saw you request, and I know and understand and fully accept your parameters, and we can talk. All right. So he sent an okay message back to Alice, and then you can establish the connections. But is there any potential issues if we just do this two-way handshake? Okay. Actually, there is some issue. So you can see it from this angle. So suppose Alice say let's talk, and she sent all the parameters to Bob, and Bob will look into that, and okay, he decided that he will accept all the parameters and capabilities that Alice may have, right? And then on the Bob side, it's just confirmed. But what about Alice's side? So if Bob sent an okay, then Alice will go to establish status. But the receiver side, Bob never know if Alice has accept whatever Bob's parameters, which is conveyed using this message okay, right? But Bob do not know if Alice accepted that or not. So because after Alice accepted, it didn't send any confirmations to Bob. So Bob don't know. So actually it's a kind of one-way confirmation instead of two-way confirmation, right? So this is a quite significant drawback that needed to be resolved. That's why we always involve a third messages. So if Alice sent a back, I'm okay, to Bob, so Bob can also be confirmed that his parameters has been accepted by Alice. So by doing this three-way handshake, both sides can be sure that everything has been agreed, right? So the handshake can be done. And also because another reason that we want to do three-way handshake is that if we do two handshake, it can be tricky because sometimes network connections, network packet can be lost, right? So if you can receive duplicate packet. So if it's a two-way handshake, it will be definitely difficult to cover those extreme cases. And the third issue, potential issues of handshake is security. By doing three-way handshake, I mean it's more secure because both ends has kind of have the opportunity to confirm and synchronize, right? Synchronize the initial connections on both sides. That's very critical. Okay. So basically, a three-way handshakes. A little bit more details about how the three-way handshake is done can be illustrated in this slide. So left-hand side is client, all right. Right-hand side is the server side. So at the beginning, they are all in the listen status. Okay. So now the client initial connection. So as we mentioned before in the TCP head field, we have 6 control bits, right? So to initial a handshake, then you have to set the sync bit to 1, which essentially means this is the handshake process to synchronize something between client and server. So it's initial stages of TCP connection. So, and also the client will select its initial sequence number X and tell the server side, right? So you basically client side goes to same sent status, and after the server receives this same key message, it will respond, right? It will choose its own initial sequence number, which is Y, okay, and send it to client with a same bit still is 1, means that it is a handshake still, right? And it chooses the sequence number Y. And acknowledgement bit is 1, which means this is acknowledgement to your previous sync message, right? This is the second message, and it tell the other side, tell the client side that acknowledgement number is X plus 1, which means I have already received the sequence of X, right? I'm expecting next X plus 1. So whatever packet you send me next, it should have the sequence number equals to X plus 1. So that's what exactly the client side will be doing. After the client side receives this message from the server side, it will establish the TCP connection. All right, this is the client side is established because it has already received the confirmation from the server side. So it will set the ACK bit to 1 without same bit, and then set the acknowledgement number equals to Y plus 1, which means I have already received the sequence number of Y, so I'm expecting next that things I'm receiving is Y plus 1, right? So it's kind of after this confirmation is received by server, then the server side is also established, right? So only after this three-way handshake, both ends are kind of confirmed and synchronized. Then they are ready to beginning sending data. Make sense? So how about we close connection? So we all know that to initiate or start a TCP connections, we need a three-way handshake, right? But how about closing a connection? Okay, so we know that one of the control bit in the six bits is control bit of header field, TCP header field. There is a fin bit, right? Fin bit is used for closing and tearing down a connection. Okay, so usually that's the bit you have to set if either side of the two peers want to finish and close a connection. Okay, so whoever received a packet with fin bit set to 1, then you should acknowledge that I received your message and I know that you are quitting. All right, and actually this process needed to be done on both sides, which means both sides need to agree that you are stopping sending data and you are ready to close the connections. Okay. So let's see a little bit more details about how the closing TCP connections can be done. So original state from the client side and the server side are all established, means that they are active TCP status. And now suddenly suppose the client want to close a connection. So basically what it will do is that it will send out a TCP packet with fin bit set to 1, right? Fin bit set to 1, which is essentially telling the server side that I, as the client side, I want to finish this TCP connection. So it will send a fin bit equals to 1 and the sequence equals to X. All right. So basically, it will enter to another intermediate status, which is the fin wait, which means I want to stop, but I cannot wait for your response. So for the server side, after it receives this information, he get it, right? I understand. So you are trying to stop, so that's fine. I will acknowledge your request. I got your message. All right. I'm not expecting any more information from you because after you send the fin bit to 1, then I know immediately you will have no more data to be sent to me. So basically, After you send a fin bit, you will stop transmission any data further. You just wait for the response from the server side, right? So the client aimed for a second intermediate wait because now this closing connections, because tearing down a TCP connection need to be agreed on both sides, right? So you are done with data transmissions to server, but the server may not have been done, yet, right? Server may have some remaining data to be sent to you, so you cannot just say I want to close and you just quit. That's not a healthy way to terminate a TCP connection. You needed to say, okay, I'm done, so I no longer have data to send to you, but if you have remaining data, please send it to me as soon as possible, so that both directions has all the data delivered, right? So it can be, can be terminated with a very good status because all the remaining data have been delivered. So no some weird situation, right? So after some times, after it enter this direction, then the server may still have the data to transmit to the sender, right? So he will get the remaining data transmitted to client, and after it is done, then the server side will send a finished bit packet, finishing bit set 1, which means that, okay, I'm also done transmitting any data from servers to client. So so they end to another status, okay? So the client will send acknowledge, okay, I got you. I know that you have done sending all the data bits to me as well, so we can officially put it at close. All right. So you can see two ways acknowledgement and confirmations to tear down TCP connections. But there's a small thing you have to be careful, which is from the client side, actually after it sent out the confirmations, it didn't stop immediately at this point. I mean, after it received the fin bit from the server side, actually it's very clear. I mean, the client side can stop right here. The client side can tear down immediately. I mean, if it leave behind, it don't care what will happen to server side. It can do this. It can just stop this. But why we take a little bit more time waiting before we officially close the TCP connection? Right here, you can see we possibly will wait more, like 2 times of the maximum segment lifetime. It can be 30 seconds, 1 minute, something like that. So do you know why? Why we needed to wait further times to officially close the TCP connection? So actually the answer is, for the final confirmation, it can be lost, right? So if it is lost, then we will run into trouble because the server side will never receive this acknowledgement, then it will just keep waiting. And from the client side, you send out, so you are done, that's fine, but it's never a healthy closing of the connection. So you have to give enough time waiting right here, a timeout right here, a timer right here, wait for the confirmation to make sure that this message has been received by the server. All right. So after that, then you can pretty much show that it has been closed from both sides. All right. So actually, this is not a very simple design. Actually, for TCP connections, there are a lot of issues needed to be resolved. So that's why if you look into the TCP standards, it's quite complicated. So it has a state machines which are many different status, and they switch back and forth, and depending on the situations, they may go to different states. So it's quite complicated. But this is a very simple illustrations of how to close a TCP connection. All right. So TCP does flow control. It also does congestion control. So you know the differences between flow control and congestion control? You do, right? So previously I mentioned that the flow control is only between the sender side and the receiver side to make sure you are not overwhelming each other, right? But for congestion control, it's about the network, which means that you are trying to do something to reduce the network load or network congestion. So it's not just overload the other end or the receiver. It's kind of to make the network working in a healthier condition. So we will be discussing a little bit more about congestion control because it's a very, very important mechanisms used in TCP. All right. So this is a key part of the transport. It is also the key part of the whole computer network classes. So I hope you pay very close attention to whatever we are gonna discuss. All right. So congestions basically you can describe it as too many sources are sending packets at the same time, and it's too much for the network to handle. Right? This is kind of network is totally burned down. So what will happen if network is very congested? So something you can expect is, for example, you will see a lot of packet lost because the network is congested and the packet spend too much time waiting in the queue, right, somewhere else in the router. So and the buffer can overflow and then it will just drop that packet. So the packet can be lost in these situations, definitely. And the other behavior, the second behavioral symptoms is that you may have to wait for a long, long time to get some kind of response, which means essentially long delays because the queuing will be taking more time. So the queuing delay will be quite significant. So as a matter of fact, the congestion control is congestion issues is a very important issue. It's top 10 computer science problems in the computer science history. All right. So you may begin thinking about these problems, how to resolve the congestion or how to control the congestions in the network. Okay. So essentially, there are two ways to do congestion controls. Okay. So before that, actually, at the top of this slides, you can see the differences between the flow control and the network and congestion control. This I will not repeat. All right. But to overcome this congestion control, there are two typical ways. It's a design decisions you have to make. So the first one is mechanisms is end-to-end congestion control. So end-to-end congestion control means that the router, the intermediate routers in the network will not do anything. All the things will be done by end host. Okay, so that's why it's called end-to-end congestion control. Okay, so basically, network will do anything. Will not do anything. There's no explicit feedback from network, and the congestion is just not something clear status that network tell you that the network has been congested. It's something that you and host has to discover or infer by yourself. For example, when you see a lot of data lost, packet lost, and you experience a significantly higher delay, then you can infer that some congestion is happening in the network, right? That's something you can do from the sender side and receive side, or this and host on your machine, on your laptop, right? So actually, the TCP takes this end-to-end congestion control mechanism, which means it's only end-to-end things. Nothing in the network is involved. So TCP is adopting these simple mechanisms to resolving congestion control. And some more advanced network-based congestion control mechanism is more advanced in the sense that not only end-to-end systems get involved, it also the routers get involved. So for example, the routers will provide very clear feedback to the end system, telling them exactly, okay, I'm the network, I'm the router, and I'm congested. I tell you clearly, and I will let you know. For example, I can maximally take like 100 kilobits per second, so you do not use some window size more than that, something like that. Okay, so for example, a typical methods of this network assisted congestion control that you can send some kind of single bit. You can, for example, from the packet you send it to the router or send through the router, it can set a bit indicating that some congestion is happening. So this essentially you are telling the end host. So whenever end host send out a packet, and it will be marked in that bit by the router and received by the end host, right? The other side. And then if the end host see that okay, this bit is marked, it means that some congestion is happening, that will reduce my sending rate. Right? How to reduce my sending rate? You still remember? I can reduce the window size, right? I can reduce the sending window size, and the rate will goes down. Okay, so you have to notice the difference between these two mechanisms. The one is the network is totally unaware of congestion. They are not participating in resolving these congestions. And the right-hand side is the network is involved, and it is clearly and explicitly telling the two sides that congestion is going on, and we have to do something about it. All right. So, if we only consider the simple case, which is TCP methods of doing congestion control, that is the end-to-end congestion control mechanism, left-hand side, right? So TCP does this, and more specifically, how the TCP does this congestion control is what it adopts is a mechanism called AIMD. Okay, AIMD means additive increase and multiplicative decrease. Okay, so it means that it is an approach that if sender didn't experience any, for example, loss or long delay, then it will just keep increasing its transmission rate by increasing the window size. So essentially, it's kind of like keep trying to reach out, to increase, to get more transmission bandwidth until the network is congested, right? Until some loss happens, I can decrease the sending speed or transmission speed. All right. So basically, there are two steps. The first step, if there is no congestion, there's no congestion happening, what I does is I keep increasing my window size. So C wind is congestion window. Basically, it's the window size you are using to sending out the packet. All right. So every time you didn't see packet loss or anything unusual, then you just do additive increase, which means that every maximum segment size you send, every segment you send out and you receive successfully, for every RTT, every round, you increase your sending windows by 1. So which means that every round, if I send 1, I receive it, and it's successful, then it means network is okay, then I increase my windows by 1. All right? So I'm sending more and more back-to-back in-flight packet in the network. And you keep doing this, So what will happen? If everybody is keep increasing, then the network has limited bandwidth, then sooner or later it will begin having some congestion, right? So what will happen is that when the loss is detected or the long delay is detected, then the congestion is inferred. Then what will happen to you that when you see some losses or long delay, then you can do, you have to react, right? Otherwise, it will be fully congested, and then will be a disaster for everyone. So what you can do is you do multiplicative decrease. So what do you essentially mean that you cut your congestion window or sending window size by half if you experience some loss. So this means that additive increase is slower. You increase slowly, but when you experience some congestion, you cut or you decrease very rapidly, right? Multiplicative decrease, you cut by half, right? That's a huge cut usually. So you can see the mechanism. You always keep trying to increase and then you decrease. So which can be illustrated in the bottom figures right here. So supposedly the y-axis is the size of the window, all right? X-axis is the time. So usually what you do is you do additive increase first. You increase your window size and your transmission rate. Until loss happens, then you reduce your window size by half, which is, right now this is Windows, right? Window size. And you reduce by half. And you keep sending out, and if no further loss or long delay happens, then you will begin this additive increase again, right? Linear increase. And if you detect some loss again, you reduce again by half. So just to keep doing this back and forth, then you can see the window size or the sending rate is approximately this saw-shaped right, lines. So you can see it's always increasing, decreasing, increasing, decreasing, right? So approximately by doing this, you can maximize the channel utilizations, and also you try to avoid any huge congestions in the network. Okay, it's a sawtooth behavior, you can see. So what you can see, that's what one question I want to ask you is from this sawtooth behaviors, what is the approximate sending rate or the average sending rate? So actually you can see if we do average, it will be somewhere in the middle, right? That's the average sending rate. Okay. So a little bit more details about the TCP congestion control as we illustrated in previous slides when we discussed the sending windows. So if we again use this diagram to show the acknowledged package and the in-flight package and that hasn't been acknowledged and hasn't been sent, right? This is a send that hasn't been acknowledged. This hasn't been sent, and this hasn't touched yet, right? So the congestion windows is basically the maximum in-flight packet you can send out, right? So essentially, what you can tell from here is that from this position, which is the last byte you send, to the last byte you acknowledge, that the distance between these two cannot exceed the overall congestion window size, right? That's basically the limit you can use for the senders, all right? And as I also mentioned, congestion window is always dynamic. You sometimes you increase, sometimes you can decrease depending on the network status. But the overall rate, when you have a window size, you want to tell what exact sending rate it is. So actually, if you have a window size, obviously the bigger the window congestion window size, it means that it's more in-flight packet in-flight packet has. It means that the faster it is sending packet, right? Remember the channel utilizations equations we discussed. The bigger the window is, then the denominators, right? The top is larger than the utilization will be higher, right? So the overall rate is going to be described or proportional to the congestion window size. So the larger it is, then the larger sending rate is. So the rate can be approximately equals to the congestion window size divided by RTT, which is understandable, right? So RTT basically is one round. You send it and you receive the acknowledgement. So one round of transmissions, that's the time you have, and you send out in total this congestion window size, bytes per second, right? This packet size. So that's basically within one round of the time, how much packet how much bits or bytes you can send out. So you divide it by this RTT, that's the basically sending rate. Okay. So you can see it's proportional to the congestion window size. The larger the window size is used, it's more sending rate, okay? And also higher channel utilization. Make sense? Okay, so for TCP, apparently we want to do additive increase but multiplicative decrease. So what if we are, for example, we will, once the original connections is established, what will we do? What's the initial status? So it's some things you have to figure out, right? So you cannot just pick in some random congestion window size you use. Usually it's started from 1, right? So the congestion windows will be starting from 1, which means that you send one packet first and you wait a response. Because you don't know network situation, right? So initially the congestion windows will be 1 and you only send one segment out and you wait for the response. All right, 1 MSS, and you wait for RTT. So what's next? Once you receive this one, then you increase every acknowledgement actually you receive, every successful acknowledgement you receive, you increase your congestion windows by 1. Right? It's when you receive 1, then you 2. You receive 1, so you increase to 3. You receive 1 acknowledgement, you increase to 4. Similarly, every acknowledgement you receive, you increase your congestion window by 1. So from the that's the every acknowledgement, all right, you receive, you increase by 1. So, but if we consider from the perspective of RTT, every round, how many congestion windows you are increasing? So you can see, you can observe from this the right-hand side picture. So originally the congestion window size is 1, right? And after one round, your congestion windows is 2. After one round, the congestion window is 4. 1, 2, 3, 4, right? So after one round, the congestion windows will be 8. So you can see, what did you see right here? 1, 2, 4, 8. So essentially every round trip times, you're doubling your congestion window sending rate, right? So this mechanism is called TCP slow start. So essentially, slow start means that it's starting from 1, right? Congestion window is starting from 1. It's quite slow, right? But as a matter of fact, it's not. In other sense, it is slow in terms of starting from 1, but it is not that slow at all, because every round trip time, you're kind of doubling your congestion window size, right? 1, 2, 4, 8. So you can see, although the beginning point is very low, but it can increase exponentially, and it's quite fast, and it can touch some kind of receiver windows, right? Some upper bound, something like that. So when we consider this slow start process in a large background, then you can see that this shape. This is an example. So y-axis is congestion windows, x-axis is time. So you started from 1, so right, it's exponentially increase actually. Every round trip time you are doubling your status. Okay? So you can see, even though it's a slow start, actually it's an exponential increase until the congestion windows touch the size of receiver window. That's something you cannot exceed, right? Still remember the receiver window? The receiver windows is for the flow control, right? So that's something the upper bound, the receiver side tell you that you can never do more than that, right? That's the upper bound that you can do. So after you reach the receiver windows, you cannot increase anymore. Then you just remain at the windows, and you keep sending, right? And then pretend, suppose at this point of time, congestion happened. For example, network situation suddenly changed or became very congested. So in this case, timeout will happen. So what will happen is that you will because it's a timeout, right? So you will reduce congestion windows back to 1. Okay. And on top of that, you will set a slow start threshold. So there's a new terminology called slow start threshold. So slow start threshold essentially is equals to half of the congestion window size when the congestion happens or when the packet loss or timeout happens. So you can see, first you'll reduce the congestion window size to 1. All right, you have to start the slow start threshold again. All right, and you are setting a slow start threshold. So you may ask why we need this threshold. So we will be discussing soon. So you are thrown back to 1. So you have to do slow start again because it's a timeout or congestion happened, right? Because sending at the maximum speed, right? So you drop back to 1, and you begin to do this slow start again, which is exponential increase, right? But this time is a little bit different. It's not gonna go back all the way back to the receive window side. Instead, you have to when you congestion window size pass this slow start threshold, you will still increase, but you will increase slower. So previously, slow start is kind of exponential increase. But if you pass that slow start threshold, you have to increase by this new number, this new rate. All right. So if you say this exponential rate increase is a doubling sending rate every RTT, then this one is slower than that. It's just 1 MSS is incremented by 1 MSS multiplied by MSS divided by congestion window size. So essentially, it means that it's linear increasing for every RTT. All right, so you can see. So you may be wondering why we want to do this. So again, so you apparently because slow start actually is quite fast, right? It's increased exponentially. So if you don't set this slow start threshold, it will touch this receiver window again, and it will make the network congested very fast again, right? And it will be dropping. So it will be back and forth fluctuating all the time, which is not good for both the network and for the end host sending things. It's kind of tripling between between 1 and the congestion window size. It's very, very unstable packet delivery. So that's why we incorporated this slow start threshold so that we can make sure that after that threshold we do a little bit more cautiously instead of exponential. We increase the congestion windows linearly, right? Right? But if the network congestion still happens in this situation, then you will do it again. You reduce your congestion windows to 1, and you do the slow start again. But the slow start threshold at this moment has to be set half of the moment, the congestion window of this moment when the congestion happens, right? And after you touch this slow start, this linear increase. Okay, if nothing happened, no congestion, you didn't do any further transmission, then the congestion window size will not be changed, right? Because it's idle interval, nothing is happening. You are not sending any data, right? So in this case, the congestion window will remain constant. It will not change until, if you begin sending again and some congestion happens, then you do this again. Okay, it's just to keep doing this. Slow start if congestion happens. Make sense? But you have to be very careful about these things because very important things to make the network kind of stable and also resolving this congestion situation. So at the beginning, the slow start threshold is equal to the receiver windows, right? So that's why you can keep increasing until you reach the receiver window. Until that congestion happens, then the slow start threshold will be reduced by half. So by doing this, we can always make sure that the network, and the sending rate is kind of under control. So if you experience a long idle time, for example, in this slide, you have a very long idle time, then nothing is being sent. Then usually in these cases, you just have to reset the windows to 1. So back to 1. That's what happens right here, right? So in TCP reality, actually, we have different terms for these two periods. So exponential period and linear period, we have different names. So for the exponential increasing rate from 1, then this period is usually called slow start. Okay, although it's not slow. And the linear increase after we hit the slow start threshold, SS threshold, usually this process, linear increasing phase or period, we call it congestion avoidance. So you can see we want to avoid further congestion, right? So we do it more cautiously, increase more slowly the compared with exponential increase. So in the real TCP, we have two different TCP versions. Actually, there are many, but two very important and very typical ones are called TCP Reno and TCP Tahoe. Okay, so you can see a little bit different from between the TCP Reno and the TCP Tahoe is that one case is different. How would you be able to handle triple duplicate acknowledgement? Okay, so actually TCP Reno only do this differently for those triple duplicate acknowledgement. For example, one packet is lost, and you don't want to wait for timeout, right? If it's a timeout, then you definitely have to do a slow start, right? But if you receive, for example, 3 duplicate acknowledgement, we want to do faster TCP retransmit, remember? And then what will happen right here is that we will do a little bit more aggressively. So from here, if we see that the loss is caused by timeout, then we will do the TCP Reno and the TCP Tahoe will do the same things. It will reduce to 1 and begin the slow start again, if it is a timeout. All right, but sometimes the losses may not necessarily detected by timeout. Sometimes it's lost, right? Then in that case, the loss can be detected by triple duplicate ACK or timeout, right? You identify the loss. So if we do the triple duplicate ACK, you see then for TCP Reno, what you do instead of going back down directly to 1, what you do is you cut the congestion windows by half, and you plus 3 additional MSS size right here. You cut by half, you add 3 additional MSS size. And from there, you begin the congestion avoidance. Okay, linear increasing. That's the same thing as these ones in TCP Tahoe. So what differences can you tell from this diagram? So the difference between TCP Reno and the TCP Tahoe, actually the only difference is what is the source of the loss. Okay, so sometimes when you see triple duplicate ACK, you know that some loss is happening, right? Or you see timeout, then you see something happening, and it seems it is a loss, right? So, but for TCP Reno, it's kind of we differentiate. If it is a triple duplicate ACK loss, then we do more aggressively. We reduce less, right? But if it's a timeout, both TCP Reno and TCP Tahoe all go back to 1 and started from 1 again. Right? So you can see TCP Reno is a little bit more aggressive in terms of handling this retransmission cases. If one packet is down, it's lost, then a couple of them is lost, you receive multiple duplicate accidents, you do a little bit more aggressive, just to try to improve the transmission efficiency. Okay, make sense? So the overall throughput, because we are having some kind of sawtooth shape for the congestion window size, and the this window size approximately is proportional to the overall sending rate or throughput, right? So for example, if we ignore the slow start, we assume that because slow start usually is very fast, right? So if something is slow start, it will always goes 1 and increase very, very fastly exponentially and back to W. So usually it's kind of, we just ignore those things because it's kind of very narrowly shaped. It will recover very soon, okay? Because it's not slow actually, right? So, but from a larger scales, the overall TCP throughput, it will behave just like this. Sawtooth shape. Okay. So suppose if we have a window size W, and then the behavior you can see if we use this, congestion avoidance, right? Congestion avoidance linear increasing, then it will be approximately the actual TCP throughput will be this shape. Although in the middle there may be some slow start, right? Gap, but we ignore those things. Approximately it will be this shape. Original is W, right? Original is half a W, you increase and you drop by half, you increase back and then drop by half, right? So actually, if we see this shape, the average window size actually is what? The average window size will be this line, right? So this line actually is averagely it's like 3/4, right? A quarter, 3/4 of W of RTT, right? So the average TCP throughput is going to be this line, which is 3/4 W over RTT. Make sense? Make sense? That's the average TCP throughput. So in reality, the TCP actually to measure, you have to, actually there are a lot of researches in TCP to measure the overall throughput. For example, we can do this calculation. If we have a 1500 byte segment and the RTT is 100 milliseconds, and we want to achieve a 10 gigabits per second throughput, then what window size do we need? So you can put all these things into this equation, right? Your average throughput, you put it right here. Window size is something you want to get, and RTT is right here. You put everything. You put RTT in, you put throughput in, you will be able to get the W, right? So that's the W's. In this specific example, the W's will be A3000, something around A3000 in 5 seconds. And then this is the case that you didn't consider the loss and the loss probability. If you do consider loss probability, then it's a little bit more complex. And as a matter of fact, this researcher, it find equations that the TCP throughput is equals to 2.22 multiplied by MSS RTT and square root of loss probability. Okay. So you can see approximately from these equations. For example, if you want to do the same, you want to achieve 10 gigabits per second throughput right here, left hand side. And you need to maintain a very low loss rate. Say it has to be less than 2 by 10 to the order of minus 10. So it's a very small loss rate, right? So if the TCP throughput is very big, and these things is kind of fixed, right? Then you probably need to have to achieve this throughput, you have to maintain a very small loss rate. This is small, then this will be big, right? Then you can increase the TCP throughput. So you can see the TCP throughput is strictly limited by the loss rate. If the loss rate is big, if it's too big, then the throughput cannot be very good. Especially this is very important for high-speed TCP connection. For example, in the backbone network, if you have many TCP and you want the TCP throughput to be very high, then you have to control the loss rate. Because if the loss rate is high, you have to do a lot of retransmission, you have to do a lot of slow start, then apparently it will harm you overall TCP throughput, right, from this shape. If you do a lot of slow start, then which means that the time you remain in this level will be few, and you spend a lot more times to do this slow start, which is below this line, right? Exponential line, slow start. Make sense? And the last topic is about the TCP, the TCP fairness. So this one is also a quite important concept, which means that whatever protocol you design, you want it to be fair to everyone. Right? For example, if you have a K TCP sessions, K customers, and they are sharing this botnet link with a fixed numbers of bandwidth supposedly to on. So whatever mechanism or protocol, TCP protocol you adopted, you approximately want that these bandwidths are to be shared evenly or fairly by this K TCP session or K TCP users. That's our design goal, right? So everyone should approximately get like R over K share, right? So that's the goal that we want to achieve by designing TCP to make sure everybody get a fair share. So for example, if one TCP connection get all of them or get 90% of them and the other ones get just 10%, it's a bad design, right? So we will tell you why the TCP we have discussed, the slow start and then congestion avoidance, why it is approximately fair for everyone, how it can be achieved. Okay, to illustrate the fairness, the TCP fairness, we use this simple example in which, for example, we have a band, we have the band that is shared by only two connections, connection 1 and connection 2, right? Very simplified version. So in reality, there can be many competing users. So if it is just the two users, then right here, so you can see supposedly the connection throughput 1, so it's x-axis. Connection 2 throughput is R, right? So y-axis. So since R the throughput R of 1 plus throughput 2 is fixed, you cannot exceed R. That's the maximum. That's the bound, right? That's the bound. These lines mean that connection 1 throughput plus connection 2 throughput is R. You cannot do better than that. You cannot go beyond this line, right? And the y-axis, this is it shows that this is a line that they have the same bandwidth, right? So it seems that our goal is to make sure that it's going something. The transmission rate right here is somewhere around this line, right? So that, for example, the connection 1 and the connection 2 will have similar equal share of throughput, right? So that's our goal, which means that no matter where you start, you want that approximately, and the throughput will end it right here. So how would you do that? In TCP, we only have additive increase and multiplicative decrease. So it needs to be converged, all right, no matter where you start. So let's pick one direction. Let's pick at the starting point. Actually, you can pick any place. So let's pick one point right here. So at one point right here is what do you see? Okay. Point right here, you see that okay, x-axis is right here, it's congestion, and the y-axis is connection 2 is this rate. So you can see because it is within this rate, which means the network has enough bandwidth. So which means no congestion will happen at this point, right? Because it's within the limit of R, right? In this shape. So which means since you have enough spaces and bandwidths, what we will do? You will do additive increase, right? So which means that both x-axis and y-axis, both connection 1 and connection 2 will increase linearly in the same speed, right? So that's the speed you are using. They are increasing in the same speed. All right. So that means that we will go this direction. We will go this direction. We will keep increasing throughput for both connection 1 and connection 2 until this. So at this point, what will happen? Actually, this point means that the sum of the throughput of connection 1 and 2 is equals to R, which means it's reaching the upper bound throughput, right? So, but if you keep reading, if you stop right here, it's fine. It shouldn't be no problem. But if you keep increasing, then congestion will happen, right? Because you are exceeding the total bandwidth of R. So supposedly congestion sooner or later will happen. Supposedly it happen right here. So what we will do? Because congestion happens, we will do multiplicative decrease, right? So multiplicative decrease will essentially mean that both connection 1 and connection 2 will reduce by half, right? So how to draw this line? So reduce by half actually is this line, right? So you have your x-axis reduced by half, y-axis you reduce by half. Essentially, it's a line that you draw from this point to the original point right here, 0, 0. And you pick the middle point right here. That's the point you will be going. You reduce by half for x and for y-axis. So you will reach to this point, and again, now if you reduce to this, then the network is fine again because no congestion, right? It's in this range. So you will recover your slow start, you begin to additive increase again. So which means that you will linear increase again until it hit another congestions and you reduce by half again, multiplicative decrease, and you linear again, increase again, and multiplicative decrease, linear increase again, multiplicative decrease, until at the least converged to this line, which means that you will go this way. You're vibrating right here. But vibrating right here, what does it mean? It means that approximately this line means that connection 1 and connection 2 will have the same throughput, right? So if you're vibrating right here, it's fine because connection 1 and connection 2 will have the same throughput. So you can see they become fail between these two connections, TCP connections. Although the starting point is not fail at all. Starting point connection 1 sending faster than connection 2, but it will converge. So similarly, if you have any starting point at any point right here, they will finally converge to this line. Make sense? So for example, if I give you some example for you to solve this problem, for example, originally I have W1 and W2, the original capacity is 10, then I give you some random numbers, so what will, so you can see after one round, 2, 3, after several rounds, it will eventually converge to the same speed, right? 3, 3, 6, 5, 4, 4, 5, 5, 6, 6, 2, 3, 3, repeat. So it's a fail, right? Make sense? So because of the designs of additive increase and multiplicative decrease, then the TCP fairness can be achieved. Approximate. Right? Remember this example, if I give you some other numbers, you make sure you understand them and know how to do this. Okay? But TCP is quite a fail. That's a good news for us. But how about UDP? We know that UDP does not have any congestion control, right? So for example, if it's multimedia applications, usually TCP will not get any control of it. It will always try its best and send with array. So that's why multimedia applications, if you want real-time messages, you cannot use TCP because TCP, you slow down, you go up, it's vibrating, then it will be a bad news for live media streaming, definitely. Okay? So instead, this you have to use UDP for live streaming. So if we put UDP and TCP together, that's what exactly happens on internet, right? The internet has TCP traffic, UDP traffic, then which one is the unfairness between TCP and UDP? So as a matter of fact, the UDP can always beat TCP because TCP has congestion control, but UDP doesn't. So UDP is always aggressive, constantly. So what can you do? So the good news is if your UDP is always aggressive, you don't do TCP congestion control. But TCP, I do congestion control, but I can do parallel multiple TCP sessions. So we can potentially increase the throughput as well, right? I can open multiple parallel connections. For example, web browsers can do this. So for example, if you have a link read OR, you have 9 existing connections. So for a new application come, and if it asks for 1 TCP, it will get rates of R by 10. But if a new application asks for 11 parallel TCP, then it will get more than half, right? So you can do this. You can try to establish more TCP connections, and you get more share. Make sense? Okay, this is the end of the transport layer. So let's briefly summarize what we have discussed about the transport layer. So for transport layer, we know that it's do multiplexing, demultiplexing. So you mentioned the UDP, tuples, TCP, 4 tuples, right, to uniquely identify socket. And we introduce the port number, and then the flow control, and the congestion control, and how UDP and the TCP checksum has been done, how the session establishment, and everything. So that's basically conclude our discussions of transport layer. So next lectures we will be discussing network layer. All right, so it's the one layer below the transport layer. So which means transport layer is depending on IP layer or the network layer, and it's the core network. All right, that's very exciting part we will be touching in the next lecture. All right, so this is conclude our lecture today. So hopefully you you get more you get what you want, you expected from this lecture. If you have any question, feel free to leave me a message, or next lectures come to in the office hour or in the lecture time, come to talk to me, and I will clarify that concept for you. Thank you, guys. Thank you. Have a good day. Bye.